Thank you. I'm Sian Jin, and glad to have this opportunity to share with you some of one of our project is to integrate the deeply integrate lossy compression with HDF5 to improve the parallel write performance. So I think the previous presenter has demonstrated very well on the motivation and backgrounds of using lossy compression towards scientific data. So I will just use this diagram again to tell you more on this project. So this diagram is fairly easy to read. So consider that we have 5 processes, and each one has 2 data fields that need to write to the storage system. And if we look at from the top group, the first one, if we write the entire data in original form to the storage system, sometimes it can take quite a long time, and it can create bottleneck for many applications. And in the second group, we can see that we can utilize the lossy compression to compress the data first, and then to write the compressed data to the storage system. And if the compression ratio is high or the compression throughput is high, then many times we can improve the performance by doing so. However, if we look deeper, then we will notice that every process will actually has to wait until the other process to finish, the slowest process to finish this compression to initiate their parallel write. This is because, as Dr. Tao mentioned, is that we do not know the compression ratio before the compression actually happens, so we don't know the offsets to where to write to for those compressed data sets. And what we proposed in this project is meaning to utilize the async vol connector of HDF5 and the predictive model that we proposed that allow us to predict the compression ratio and the compression time before the compression actually takes place. So that allows us, as we can see in the third group, is that we can overlap the compression with I/O. Of course, along with other designs here. But in this case, we also find that once we do this overlapping with compression and I/O, the compression order actually matters. So which data fields to compress first is actually going to affect our performance improvement. So we also propose several algorithms to schedule the compression order in order to further improve the performance when we overlapping the compression and I/O. And furthermore, in the fourth optimization, we propose the fine-grained compression, which is not just cutting the data into smaller blocks, but we also propose several designs to overcome some of the overhead that is created because of the fine-grained compression. For example, we use shared Huffman tree in order to improve the performance for lossy compression when compressing very small data blocks. And this will efficiently improve the overlapping efficiency between compression and I/O. And the last optimization is more interesting, that we propose not only to overlapping the compression I/O, but also with the computation. So we noticed that many simulations can shift it to GPU computing, and this gives us the opportunity to use CPU and background thread to perform the compression and I/O. And we propose to overlapping all 3 together, of course, with the optimization algorithms. So the real implementation is not as ideal as what this diagram shown, but as you can see on the right-hand side, this can significantly improve the performance of parallel write in this case. And some of the limitations and the future work of this project, first of all, is the prediction is not always accurate, and also the system will create uncertainty, and both of which will delay some of our scheduled compression, or I/O will eventually create a larger overhead in many cases. So what we can do is to propose a more accurate prediction, especially for lossy compression, and also to create our framework to be more robust to this kind of, to tolerate more on this kind of error. And also we would like to provide an uncertainty analysis for the scientists and the users. For example, we want to give a statement like we expect to improve the performance by 20%, and we can guarantee that 99% of the chance the performance improvement will be within, say, 10 to 30%. So this kind of statement. So I think this kind of statement can be very helpful for the scientists and to the users. The other thing that currently is not very user-friendly, so not like the compression filter that you can just use on whatever data that is already using HDF5, but here is kind of hard to use. So we are developing a new API that is similar to the async vol connector from HDF5 that introduces several new inputs to this API, for example, additional config file that takes some offline profiling results, and also the user-defined error bound or data quality. So note here that the user can define not only just the error bound, but also the data quality, because we also have studies on transferring the data quality to the optimized or adaptive error bound. So we call the adaptive error bound selection module. So hopefully this can be easier to use in the future. And that's a very brief introduction of this project. Hopefully that can bring you some insights of that. And thank you.